Hello and welcome to the first video in my series for week 2. You can see that we're going to cover properties of exponents, scientific notation, radical expressions, and working with complex numbers. And I hope you watch each of the videos in the series. I would give you chocolates if I could for watching. So let's get started. Let's first talk about some properties of exponents. All right. I can give you a bunch of rules to memorize, and for some of you, you'd feel very comfortable if I did that, but I always want you to understand the logic behind something, if possible. So I like giving you the why and then the rule. I think it's going to make a lot more sense. So basically, if you have x to the third times x to the fifth, what you want to do is add those exponents. So we would get x to the 8th in that example. The reason we want to add them is because what we have is x to the third, which means x times x times x. And then we have x to the 5th, which is x times x times x times x times x. And altogether we have 8 of those x's. So you can see if we get bigger and bigger, we're not going to want to write all that out and count up all the x's or whatever. So remembering this rule will help you. And the more you work with this rule, the more you'll find you're remembering it without even realizing it. So we have to have the same base, and then all we have to do is add the exponents. So for example, b, it would be 6 to the, and you're adding, I hope, 7 plus 2 plus 3, right? So you have 12. So hopefully you got that. And I have other examples, and remember, all of these examples are in the PowerPoint presentation and doc sharing. My videos are fairly short, but hopefully you'll take a little extra time and go look at the PowerPoint presentations, because you'll see tons and tons of examples there that'll be really helpful. All right, so I didn't show the slide for the product rule, but all it says is a to the m times a to the n equals a to the m plus n, but we just worked on examples for those. So if when we multiply with the same base, we add the exponents, what do you think we do when we divide? Subtract. That's pretty logical, right? So let's go right to some examples. So example A would be x to the 6th, because we're just subtracting. We have the same base. Now take a look at example D. I'm going to go to the next slide for that one. What some people do is they think that all new rules apply even to things that you've already learned. That's not true. In other words, 6 over 4 will reduce to 3 over 2, just like you always have done with fractions. But we are going to look, and I'm going to erase here so it's a little easier to see. We are going to look at the r's and then the t's, okay? Because remember, if we're going to use this rule where we subtract the exponents, we have to have the same base. So r to the 7th over r to the 3rd is r to the 4th, because we subtract the numerator's exponent minus the denominator's exponent. And then for t, it's very tempting to say, oh, well, that's t to the 9th. But remember, the t in the denominator there has an implied power of 1, so that would be t to the 9th over t to the 1st or t to the 8th. And that makes this our final answer for that problem. Okay, the exponent 0, big, big, big concept here. Anything raised to the 0 power is 1, always, always, always. I'm going to show you why. Let's say I had a to the 2nd over a to the 2nd, sorry. Okay, and if I were to write that out, I would have a times a over a times a. And if I decided, I'm going to get another pen color here. Let me get blue. All right, what would happen was I would just cancel, 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 cancel. Basically, I have a over a, which is 1, a over a, which is 1, so I've got 1 times 1, which is 1. Everything canceled out. That is always what happens when you raise something to the 0 power. Okay, that's kind of what happens in the background. All right, so we can also notice that, well, we can use our rule, right? And when we have a division problem with the same base, we can subtract. A to the 2 minus 2 is a to the 0, which we know from all that canceling, that's equal to 1. And that is always the case. All right, so everything raised to the 0 power, no matter what it is 1. So let's look at these examples, because all of these answers are not going to be 1, believe it or not, even though they look like it. All right, well, let's see. let's take a look at example A. That's equal to 1 because that's something raised to the 0 power. That's equal to 1. That's equal to 1 because the whole thing is raised to the 0 power. D is not equal to 1 because only 8 is being raised to the 0 power. So what we have is negative 1 times 1, and our answer for that problem is negative 1. All right, and example E, believe it or not, is the exact same thing. What I want you to see is that negative 8 to the 0 power is not the same thing as negative 8 in parentheses raised to the 0 power. It's kind of strange. It takes some getting used to. And this is true no matter what the exponent is. That exponent only goes to the number it's attached to, or the variable it's attached to. All right? If you want it attached to that sign, you have to put it in parentheses. So that's the same thing. Example E is the same thing as negative 1. Okay? All right, now the power rule just says that when you raise a power to a power, you multiply. Okay? So if we had x to the third to the fourth, what that means is x to the third times x to the third times x to the third times x to the third. And you could add all those and you would get 12, right? Because when you multiply, you add. But this is, again, a little bit of a shorthand. So if you raise a power to a power, you can go immediately to just multiply. All right? And example B is 4 to the 16th. All right, if you have parentheses and two things or more inside, it's raised to a power, it's the same thing as applying that power to each thing inside the parentheses, assuming they're multiplied together. If they're added together, no. Okay, so example A would be 3 to the fourth times x to the fourth, or simply 81 times x to the fourth. If it's something you can simplify pretty easily, go right ahead and do that. And you see other examples, and all of these are in the PowerPoint presentation. And likewise, if you have a fraction raised to a power, that's the same thing as the numerator raised to the power over the denominator raised to the power, like you see here. Pretty simple examples, probably. W to the third over 4 to the third, which we could write as W to the third over 64. And again, tons of examples waiting for you. This is slide number 17 in the PowerPoint presentation. You can print that if you'd like to. The bad thing is it takes up the whole sheet of paper, so it's kind of large. But what you can do is just not replace, but you can kind of write on to the side of each one an example. And there's plenty right in this PowerPoint presentation. And I think having all the rules together might help you. You're going to find, though, as I've said before, the more you practice with these, especially in your homework, you're going to get so used to it, you're going to stop needing this. Okay, but it's available to you if you'd like it. All right, big idea, negative exponents. Negative exponents, they're treated sort of like a fraction that's not reduced. If you get a negative exponent in an answer, it doesn't necessarily mean you've made a mistake. It just means you can go farther with it. So sometimes you can see the directions say, okay, leave it with a negative exponent. But most of the time you won't. And if you don't see anything, know that a negative exponent is kind of bad form. Okay, so you won't really get it correct if you should have had it in a positive form. It's super easy to work with. You just have to get used to it. Basically, if something is raised to a negative exponent, you flip it. Okay, I know that sounds too easy to be true, but it really is. There's really no math involved. So if you look at example A, that's like m to the negative fifth over 1 right now before we start. And if I want to make it, rewrite that with a positive exponent, I just flip it, and I have 1 over m to the positive 5, like you see here. Likewise, example B is 5 to the negative 2 over 1, flip it, and it's 1 over 5 to the positive 2, or 1 over 25. And that's really all there is to it. I do want to show you example D, though, because I'm going to write the 1 under it just for my eyes. Some people flip everything, and they would write 1 over xy, and that's incorrect, because x is not being raised to a negative power, right? X is just x to the first, so that's fine. It's going to stay where it is, but y is raised to a negative exponent, so it's going to flip and go to the denominator. That's an understood one, positive 1 right there, and that's why this is our final answer for that problem. So it only flips if it's raised to a negative exponent. Okay? And sometimes you're going to see negative exponents in the problem, but you're not going to get a negative exponent answer, like looking at example B. I'm raising a power to a power, I multiply, and I would get x to the 12th, and I'm done. So as scary as it might look at first, when we simplify a little bit, it actually ends up not being that bad. Okay. And looking at example F, for example, you could flip both of them because they're both raised to a negative power. Okay. And I want to jump back up to example D, a to the negative 5th over a to the negative 6th. I'm going to subtract, and I get a to the negative 5 minus negative 6. Big idea. Remember, if you see minus minus, that turns into a big fat plus. Okay, so I have negative 5 plus 6, which ends up being a positive 1. There's nothing to flip. All right, and if you have a numerator raised to a negative power and a denominator raised to a negative power, you just flip them both, like you see here. But look at that y. The problem is y to the third, and that's fine the way it is. So y to the third will stay in the denominator. It didn't have to move, so hopefully that makes sense. Okay, and same thing here. If I have a fraction raised to a negative exponent, I can just flip it, and then it's raised to a positive exponent, like you see here. All right, so that's all with the exponent rules. I am going to stop this video, and you can now go ahead and take a look at the scientific notation video.